So today is February 19, 2015, and we're going to start a new section. It's going to be on exponential functions. Last week, or actually yesterday, we ended our rational functions section, okay? So what I would like you guys to do is with the handout that you received when you walked in, you're going to go ahead and write down these notes as we talk about it through the PowerPoint. The first thing I'd like to go over with you guys is page 1. Okay, an exponential function is a function of this form. Okay, so you see that on your handout. It has a couple of restrictions. The restrictions are that b must be greater than 0 and b cannot be equal to 1. So go ahead and fill in those blanks in your notebook. Okay, and there's also some vocabulary words. The letter B, the green one, stands for base. And the h, x minus h, the whole thing, is going to be your exponent. So you have a blank space for exponent, a blank space for base, a blank space for greater than 0, and not equal to 1. Okay? Can I move on to the next slide? That's a picture of what an exponential function looks like. It usually is flat at the beginning, grows very slowly, and then just takes off at some point. Okay, so it grows really, really quickly. In real life, can you come up with some examples?
A roller coaster.
A roller coaster. What else? Good. An airplane. That's a good one. An airplane goes along the runway right until it finally takes off into the air, and it has to pick up altitude really quickly. What was the other one? What's that? Oh, gas prices. Like an amusement park, right? Yeah, I would say that. You're supposed to be falling at the speed of gravity, right? Según esto. Another one would be, you said a kite. What about a virus or bacteria? Doesn't a cold, like the cold or the flu, spread really, really quickly? Okay, it's slow at first, right? The first person has to get sick, and then I pass it on to Philip, and then Philip passes it on to the next person, but I'm already passing it to the other students around me. Okay, and so before we know it, everyone in the school is sick. Okay, so that's an example of something that grows very quickly. That's an exponential function. Let's go to the next slide. It says example, f of x is equal to 2 to the power of x. So in your table of values, I want you to go ahead and fill in the input. So our input is let x be equal to 1. Okay. So what you're going to do is you're going to substitute a 1 wherever you see an x. So what is 2 to the power of 1? 2. Good. I want you to now substitute in 2. Let x be equal to 2.
Wait, right here?
Yes, in your table. So what's 2 to the power of 2? 4. Okay, so your input is 2. You substitute that into your equation. 2 to the power of 2 is 4. That's your output. Yeah? Yes. Okay, now I want you to do 0. Let x be equal to 0. So that means you have x as the exponent. What's 2 to the power of 0?
0.
Not 0, but 1. Okay, 2 to the power of 0 is always 1. 5 to the power of 0 is 1. 100 to the power of 0 is 1. Okay, it's one of those rules that you kind of have to remember. If you don't believe me, you can put it in the calculator. Nothing bad happens when you put that in the calculator. Not like no holes, nothing blows up, you know. No kitties die. And they're saved, okay? Now I want you to let x be equal to -1. If you let x be equal to -1, you're going to substitute a -1 in your exponent. But we don't like negative exponents. We have to get rid of them. In order to get rid of a negative exponent, you have to flip it over, okay? Do we know what 2 to the power of 1 is? 2. So I just write 2 in the bottom. Okay? Let's try another one. What if I have x is equal to -2? I substitute a -2 wherever I see an x, But since it's a negative exponent, I have to flip it over. So 2 to the power of 2 is in the bottom, but do I know what 2 to the power of 2 is? It's 4. So there's your fraction, your new fraction.
So every time it's going to be the 1 on top.
If this was 2 over negative 2 over 3, then it would be a 3 instead of a 1. But since there's nothing there, we assume that it's 1. Good question. They actually asked that question last period too. Okay, so there's a picture of what 2 to the power of x looks like. It's very slow at the beginning, and then it just takes off after a certain number, okay? All right, let's go to the next slide. Transformations. Think about all the functions we have studied. We've studied quadratics, square roots, absolute value functions, linear functions, and now we're going to talk about exponential functions. What do you think h does to the graph? It's kind of recalling the information. What does h do to the graph? Moves it to the left or to the right, okay? Good. So you're going to move the graph to the left or to the right. In this case, when you're talking about h, you have to talk about positives and negatives, okay? What does h have to be in order for it to go to the left? It has to be positive, okay? In order for it to go to the right, it has to be negative, okay? H is the weird one. It's always opposite of each other. Then what about k? Good. The graph moves up or down, depending if k is positive, it moves up. If k is negative, then it's going to move down. Okay, let's go to the next slide. So let's practice. If you have y is equal to 2 to the power of x minus 2 plus 5, what is the value of k? I'm sorry, my bad. Since h is equal to what? H is equal to a positive 2, so you're going to go ahead and write in 2 in the first blank. Then the graph moves, what goes in the next blank? 2 units to which direction? To the right, okay? 2 is, it looks like a negative 2, okay, but it's actually opposite. It's a positive 2, so that's why we're moving to the right.
So 2 in the graph moves 2 units, right?
Yes. So since h is equal to 2, then the graph moves 2 units right. At the bottom, since k is equal to what? 5, then the graph moves 5 units up. Remember, k is up and down. Okay, let's try that one. Y is equal to 2x plus 3 minus 6. What is the value of h?
Negative 3.
Negative 3. Very good. So h is equal to negative 3. So then that means that the graph moves 3 units to the left. Good. And how many units down? 6. So since k is equal to negative 6, then the graph moves 6 units down. Okay, your turn. I want you and your partner to practice and fill in the last one, number 3. I'm going to give you a minute to do that. Okay, guys, so what is the value of h? H is equal to negative 2, so then that moves the graph 2 units to the left. Very good. And k is equal to negative 3, so it moves 3 units down. Perfect. Okay, let's talk about domain and range. If you guys will turn your page to the back. These are examples of exponential functions, okay? What do you notice about their behavior, their end behavior?
It goes down? No.
It always shoots right up.
It always shoots straight up. This one's not shooting straight up though. It's shooting down. But
It dramatically increases or decreases.
yeah, they're really close to the x or y axis, and they do dramatically increase or decrease very quickly, okay? If I were able to extend my graph all the way to the left over here, would I have a graph all the way to the wall, to the next room, to outside the building? Yeah, forever, right? It goes on forever. So then I'm moving in this direction towards the right, and it's going to go up forever. Okay, it's going to go through the ceiling. If we had a 3rd floor, it would go through the 3rd floor all the way into the sky. Okay, so what would be, if the graphs go on forever in the negative and positive direction, what is the domain? All real numbers, perfect. All real numbers or negative infinity to positive infinity. So every number you can think of, it goes forever in both directions, okay? Now, what would you say about the range? What would be the range? Yes, range is the y values, but are the range the same for each one?
No.
No, that one changes a little bit, okay? So the range depends on the function. The domain will always be all real numbers for exponential functions because it extends. Remember it says y because it extends. The graph extends forever in both directions, negative and positive. And the range, it depends. If it's high or low, your range is going to, it's kind of like an asymptote, horizontal asymptote. If the graph is down here below the x-axis, it's going to be from -3 to positive infinity. If the graph is up here above the x-axis, then it would be like +3 to positive infinity. Okay?
So for the y meantime now, we're cool. It depends on the
Depends on k. Okay, so the general form is simple enough, but what do the a and b do to the graph? Okay, so let's investigate. Let's change the base b first using positive numbers. So if I have 2 to the power of x, 5 to the power of x, 15 to the power of x, what pattern do you notice?
The bigger the number, the closer it gets to the y-axis.
Good. That's a very good. He said the bigger the number, the bigger the base, the bigger it gets, the closer it gets to the y-axis. What else?
The faster it increases.
The faster it increases? Okay, good. Getting closer to the y-axis. The y-intercept, do you see that it stays the same? That's a really good one, okay? So the b determines how fast or how quickly it grows, okay? So would you consider this exponential growth or exponential decay? Growth. So in that first box, you're going to say if b is greater than 1, then we have exponential growth. If b is between 0 and 1, can you anticipate what's going to happen?
Okay.
You're going to have exponential decay. So notice it starts really high up in the negative direction and starts going down. It's like the roller coaster. You're whee, okay, going down the roller coaster. So what do you think happens? Why do you think this happens? No? No answers? This is exponential decay. If b is a fraction, then your values are getting smaller and smaller very quickly. I'm almost done, okay? Hang in there with me. Now let's see what happens if we change a but fix b. So b is going to stay the same, but we're changing the a. Now what's changing? The y-intercept. The altitude is changing a little bit, but it's changing more specifically on the y-intercept. See how this is 10, this was 1, and this is 5. So the letter A determines your y-intercept. Thank you. So what changed? The y-intercept. Exponential growth or exponential decay? Yes, this is exponential growth. What do you think will happen if we make a negative? Yeah, good. Let's see what happens. If I change it to a -1 or a -5 or a -10, all of my graphs end up reflecting over the x-axis, okay, and end up going down. Exponential decay. Were you correct?
Yes.
Yes. Okay, so this is exponential decay. If a is greater than 1, then we have exponential growth. If a is less than 0, then we have exponential decay. In your own words, define exponential growth. In your own words, define exponential decay. So after answering in your own words what exponential growth and decay is, let's go ahead and wrap up our lesson. Why the restrictions? We have to have restrictions at the beginning. B cannot be less than 0 and B cannot be equal to 1, because if B was less than 0, we would have some really funky things happening. It would be from -2 to a +4 to a -8 to a +16. Is that the behavior of an exponential function? Does it go up and down like that? No.
Right there, right?
Yes, you should copy that onto your little table. No, what happens is that usually you have a like a slow beginning and then a fast decay or a fast growth. I'm going to go ahead and graph that here. Does that look like an exponential function? No. And what we graphed was the 0.1, -2, because that's your input and that's your output. Then we graphed 2 and 4. Then we graphed 3 and -8. Okay? So the graph does not look like an exponential function. Can I go to the next slide? Okay, and then the very last thing, what about b cannot be equal to -1? If we let b equal to -1, what do you think we're going to have? 1 to the power of 1 is 1. What is 1 to the power of 2? 1. Because that's 1 times 1.
They'll all equal the same.
They'll all equal what's the same? What number? 1. So no matter what my x value is, my input, my output will always be 1. So b can never be equal to 1, or else you're going to get a straight line. Okay? Does that look like an exponential function? No. That does not look like an exponential fraction, because it's going to keep going forever at 1, 1, 1, 1, 1, 1, 1. That is not good. So we have to have the restrictions. Okay? In conclusion, we can only have exponential graphs with the set restrictions. I want to thank you guys for your attention. Thank you for being such a good class.